Good afternoon guys, and welcome to today's worked exam answer video. Today I'm having a look at what could be either an AS or an A2 question from an AQA paper, focusing on first of all an ideal gas calculation and then focusing on a kind of moles, mole ratio, limiting excess sort of calculation at the bottom. So two-parter here. We can see that the first part's worth 5 marks, the second part's worth 2 marks. If this were to appear on an A-level paper in the summer, you wouldn't be getting 5 marks for the first part of the question, I'm very sorry to tell you. And this is why this question is probably from an AS paper, and I know the AS exams are obviously coming up soon, so wanted to cater for both sets of viewers today. So thinking about the first question, we are injecting a liquid, Y, into a sealed flask under a vacuum, and when it's inside the flask the liquid turns into a gas, and then obviously that gas occupies a certain volume inside the flask and exerts a certain pressure whilst inside the flask. We've got a little table of data, and then we get given the gas constant a bit further down, and we have to calculate the relative molecular mass of Y. Now this is going to involve combining two equations together, and I certainly wouldn't be combining them together within the question as such. I would be doing them as separate steps, but it's always helpful for us to recognise, I guess, which different equations we may need to use. So when we're given the gas constant, certainly in a year 12 question that's going to be related to PV as nRT. We've also got a pressure, a volume and a temperature as well, so that might be the first thing that we choose to write down. PV equals nRT, and then if we're wanting to work out relative molecular mass, that's where the mass here comes in. We can rearrange this to get moles, and then MR is mass over moles. And we could, in theory, kind of sub in and everything, but I personally am just going to work out moles, and then I'm going to sub it into here to get the MR. Now, the annoying thing about questions like these, as I'm sure you've encountered, is the units of the different variables given will often be incorrect, and it's being able to spot which ones are correct and which ones are incorrect and make the necessary conversions. So pressure should always be in pascals, and we have been given it in kilopascals. The volume for an ideal gas calculation should be in meters cubed. Everything else it's decimeters cubed, but here the volume needs to be in meters cubed, and of course we've been given it in centimeters cubed. They have given us the temperature in Kelvin, which they won't always do. If you get given it in degrees Celsius, you would have to convert it into Kelvin by adding 273, but here temperature's sorted. And then mass, with the exception of a time of flight calculation where it's in kilograms, every other mass should be in grams, and they will often give you masses in milligrams or ask you to give your answer for a mass in milligrams, so that there is another conversion there for us to do. So those are the 3 units I'm going to have to convert. I'm going to need to rearrange my PV as nRT equation, and lots of students find it helpful to kind of write down what from the PV equals nRT equation they have in the right units before they then rearrange and sub in. You can find your own method, but it does say show your working, and you will need to show correct methods to be able to get full marks, even if you get the answer right. So just think about how easy it is for someone to read your working out. So I normally do all my conversions before I then rearrange and sub in, so that it's clear that I've known to do that, and then I'm not having too busy a kind of working out area. So my mass, I'm going to need to do 717 divided by 1000 to give me 0.717 grams. which we'll need in the second part. My volume, to get it from centimetres cubed into metres cubed, I need to divide by 1,000,000, which gives me 4.82 times 10 to the minus 4 metres cubed. And then to get my kilopascals into pascals, I need to times by 1,000. So 51,000 pascals. Now I'm going to rearrange my PV as nRT, so we're going to need to work out moles. So moles is equal to PV divided by RT. And now I can sub in the values that I have deduced after my conversion. So pressure's 51,000, volume is 4.82 times 10 to the minus 4. And then on the bottom of my fraction, we've got the gas constant, which you will always be provided with. So you don't need to memorise that, although some of you probably already have. And then temperature, we didn't need to convert, so 297. Put that into your calculator and that should give you a value for the moles. And I get that to be 9.96 times 10 to the minus 3 moles. And then from there, we can work out the MR by doing mass divided by moles. We've already converted the mass, so 0.717 grams divided by 9.96 times 10 to the minus 3 moles will give me my MR. Now it hasn't told us how many decimal places or significant figures to give our answer to, but whenever we are quoting a relative molecular mass or a relative atomic mass, we should be looking to go for 1 decimal place. So the answer I get on the calculator is 71.987885, and there's nothing wrong with writing that in the first instance, kind of but then I'm going to quote my final answer to 1 decimal place, which would mean I'm going to need to round that up to 72.0. And even if it is 0.0, it's really important if we're going for 1 decimal place that we actually put that 0 on there. Okay, and that's 5 marks, which like I say, you probably won't get on that on an A-level paper. You'd probably get 3, I would suggest. Something else that they may do with PV as nRT is they might get you to work out the moles of a gas and then have some sort of balanced chemical equation whereby you then use the moles of gas produced, for example, in a chemical reaction and the mole ratios from the balanced chemical equation to figure out the moles of something else, then use the moles of that with a mass of that to get an MR, or use the moles of that and the MR of that, to get a mass. So we can also build in mole ratio questions to PV as nRT as well. So for those of you in year 12 kind of plodding on with doing amount of substance questions, be prepared to connect or link using the same question different kind of approaches, different equations, different skills. Okay, it won't always be as straightforward as just doing PV as nRT. Okay, second equation, or second question rather, we've got another experiment we're completing within a flask. We're doing a combustion reaction. So first of all, it says that they remove all of the air from the flask, and then we're adding 0.0010 moles of 2,2,4-trimethyl pentane, which has the same molecular formula as octane. We're adding 0.02 moles of oxygen to the flask. We enable complete combustion to occur, and then we cool the mixture back to the original temperature. And that's important because if we hadn't have cooled it down, the water, which is a liquid at the original temperature, could have been a gas. Why is that important? Because our job is to calculate the amount in moles of gas in the flask after the reaction. Now, at GCSE, I mean, not all the time, but a lot of the time at GCSE, it was just, here's how much of this you have, here's how much of the other thing you have, and it was always assumed that you would be given the exact amount needed for both things to be fully reacted away. It's not really the case at A level. Often they will give you one substance in excess, and part of your job is going to be to work out which substance is in excess. Now, that's exactly what we've got to do here. So I like to use the equation as kind of like a setup for a little table whereby I can then write in the moles. So we've got the moles in the question, we've got the 0.0010 moles of the C8H18, and then 0.02 moles of oxygen. So I'm going to write those in underneath each of the reactants. And at the beginning, there will be no moles of either product. Now, I've got to work out whether the 2,2,4-trimethylpentane or the oxygen is in excess. Now, there's two ways I can go about doing this. I could take my 0.001 and times it by 12.5, because the ratio between the C8H18 and the O2 is 12.5. So if I want to know if all of these 0.0010 moles will be reacted, I can times it by 12.5 to see how much oxygen I would need to do that. And to react all of this away, I need 0.0125 moles of oxygen. And 0.0125 is smaller than the amount of oxygen that we have. And that therefore tells me that the oxygen is in excess. Conversely, I could do the 0.02 for the oxygen moles and go, if I want to react away all the oxygen, divide that moles by 12.5, and that would then tell me how much C8H18 I would need, which is 0.0016. I don't have 0.0016, I only have 0.0010, so that would then show that this is limiting, and again, thus that the oxygen is in excess. So that's important for two reasons. One, because it tells us that all of the C8H18 will react away, but also it's going to enable us to work out how much of the O2 is in excess, and that's important because we have to work out the amount in moles of gas in the flask after the reaction, which will include any excess oxygen because that is a gas. So we're not going to have any of the C8H18, the 2,2,4-trimethylpentane, that has all gone. There's none of that left. But there is going to be some oxygen left, and the amount of oxygen left will be 7.5 times 10 to the minus 3 moles, and that was how much was in excess. And then when it comes to figuring out how much CO2 is made, which is our gaseous product, the water is a liquid, so we don't need to, essentially don't need to include that, but in other questions we might. We never use the moles of something in excess to then work out the moles of something else. So we are going to use the ratio between the C8H18 and the CO2. That's a 1:8 ratio. So we are going to make 0.0080 moles of CO2, aka 8 times as much as the C8H18. A bit of a tongue twister. So that's how much CO2 in moles is made, and if we want to calculate the amount in moles of gas in the flask, we then just need to add those together. So we will have the excess oxygen that has not reacted, and we're going to add that to the moles of CO2 that we made, and that will give us the total moles of gas in the flask, 0.0155. If we'd have left the mixture warm, i.e. above 100 degrees, and the water was a gas as well, we could then go, okay, ratio again from the C8H18 to 9 lots of water is 1 to 9, times the 0.0010 by 9, and then added that to our total. But the water is a liquid and we're asked for the amount in moles of gas, so we ignore the water in this particular question. Final answer therefore, 0.0155 moles, which is a combination of the excess oxygen and the CO2. Hopefully that makes sense. If anyone has any questions about these two particular calculations or any other calculations, or there's other examples you would like me to do, please just let me know. More than happy to help, do more videos, answer questions in the comments, whatever you guys need. I hope that the revision is going well so far, especially those of you who've got the AS exams coming up very soon. And if there's anything more I can do, just let me know. Thanks so much for watching, guys. I hope you have a lovely rest of your bank holiday. Bye!